So just to kind of recap what was going on here, we were talking about, using the matrix inverse to justify Gauss Jordan elimination. And we'll start with some matrix A, right? The form with some equation x plus 2i equals 5, 3x plus 4y equals 11, some system of equations. And we'll extract our matrix A from the coefficients in front of our standard form like I have done in my other video. So 1, 2, 3, 4 is your matrix A, 5, 11 is your column vector. Now, if we were just doing Gauss Jordan elimination, we'd say, okay, but why can't we just write it notation-wise? It would be inaccurate to say that that's a solution, right? It doesn't work that way. So what's really going on? What's going on is that over here, once you use Gauss Jordan elimination on vector A and get this to be ones and zeros, because you need what we call pivot columns. And pivot columns need ones in your diagonal and zeros everything above and below it. And then you found the answer, and your answer will be simplified out here once you've run Gauss Jordan elimination. But I'm going to show today why Gauss Jordan elimination works by justifying it using the inverse matrix method. So once we find the inverse matrix, anytime you take the inverse of something, you'll nullify it. So you'll just get the value 1 times the x vector here, and that just leaves you with the x vector. But if you do it on this side, just like in algebra, this is algebra after all, you got to do it on this side too. So you've got your inverse matrix times your column vector b that you started with 5, 11. And so your answer will be of this form, right? But we have to get everything in ones. And so what we're going to do is we're going to prove that by putting an identity matrix over here, right? And once we get this to be ones and it's zeros there, this is going to change everything in here. That'll be your inverse matrix, right? And just so you're aware, if you multiplied, those together, you would get, well, if you had, again, multiplying something times its inverse is just going to leave it equal to itself, or 1 in this case in terms of matrices. So to kind of, so let's go ahead and start, right? And after that, we'll just do Gauss Jordan. But what I'm trying to show is that if you just ran Gauss Jordan elimination, then everything you did to get these pivot columns this way is everything you're doing there. So it's kind of like you're doing the inverse matrix, but everything you've done to the inverse matrix, you're also, every operation is conserved. That means if you had like row 1 plus row 2, it's going to the new row 1, and then if you had like maybe row 1 plus row 2 goes to row 2, whatever the case may be, every single operation is conserved. So if you multiply that inverse matrix times b, you'll get your answer 1, 2. Or if you just do Gauss Jordan elimination, you'll also get your answer 1, 2, because every operation is conserved. So if you augment it with b, then everything you're doing here, you're also doing here. Does that make sense? But I'm going to show that with the inverse matrix method. And so in order to kind of highlight what's going on here, let's kind of begin. So we've got our 1, 2, and we need the inverse matrix for this. Let's start out like so. Oh, I'm sorry. We need to augment that. I'll try to use brackets to keep it, here. Now, I could prove this by showing like that this happens to vector b all the way through, but I might do that on another video. So what I'll do in this case, we'll just do the A inverse, but we haven't found A inverse yet. We've got to use Gauss Jordan elimination to do that. I'm just going to say Gauss J to get A inverse. So the first thing, we already have a pivot column here. So we're going to say we've got this operation. I actually might show it in the video. We're going to say that -3 row 1 plus row 2 changes to row 2. Okay? And so what that means is nothing changes in row 1 because we want this to happen. So then we do that. So that's going to give us 0 here. Nothing changed here. Nothing changes in row 1. And so we've got negative 3 times 2 is negative 6, and 4 gives me negative 2. And if we did negative 3 row 1, then we would have negative 3 down there. Negative 3 times 0 plus 1 is just 0. That changes nothing. And we have this so far. And look, we've got our 1, 0 that we needed. Do you see that?
Wait, so you multiplied 3 by 2 and then you got 6, right? And after that, what you do? And after that,
Yeah, we're just getting that 1 and 0 there, okay? We have to have, remember, if we have, our solution needs to go from this to that becoming the 1s and 0s. You'll see in a minute. If you're confused now, don't worry about it. So let's divide row 2 by negative 1 and see what we get. This stays the same. We just do this. 1, 2, 1, 0. If we divide this by negative 1 in row 2, it changes to row 2. So that just gives me 0 there, which is nice, right? And then divided by, I should divide by negative 2, I'm sorry. Let's divide that by negative 2. Jeez, let me do this real quick. Yeah, we'll divide that by negative 2 in row 2, that gives us so 0. Negative 2 divided by negative 2 is 1. Good deal. And then you're going to have 3 halves here, and then 0 there. But we need a 0 here, don't we? Now we need a 0 in entry, let's see, 1, 2. The ith row, jth column, 1, 2 is the entry there for 2. We don't need a 2, we need a 0 right here. So what we have to do now is we have to take negative row 2. In fact, we say negative row 2 times 2. So negative 2 times row 2 plus row 1 goes to row 1. So that's 0, 1, 3 halves still, and 0. It's going to go to row 1. I need to change this color. I actually meant to do that. Something different here. I don't know. It's magenta. All right, that's my next operation. I'm just going to keep the same color though. So if I do that, negative 2 times 0 is 0. So that stays 1. Negative 2 times 1 is negative 2, but plus 2 makes this 0. And then negative 2 times 3 halves gives me a negative 3 plus 1. So that makes that a negative 2. And then that would still just be 0, I believe. Am I doing something wrong here? Oh, wait a minute. What happened? Negative 3. Oh, my goodness. I made a mistake. That mistake was, that can happen. Earlier on.
does it have to be 1?
Yes, good job, Padawan. And if I did row 2 divided by negative 2 to row 2, it would now be negative 1/2. And what did I do down here? Negative 2 times root 2 to row 1. Yeah, so that changes everything. But that stays negative 1/2. And this gets the magenta. So negative 2 times, again, the 3 halves gives me negative 3 plus 1 gives me negative 2. And then the negative half times negative 2 gives me 1, right? Plus the 0 should just give me 1 here, I believe. And so that should be the inverse matrix. Well, let's take a look. Yeah, that is correct. We did it. We did it. We found the inverse matrix. So now if you end with the identity matrix, call it I2. And their identity matrix look like these. Like this is what you wanted in the end, be things like this. This is an identity matrix because it changes nothing. So this is going to be a 2 degree, this is a third degree. And once you've gotten that identity matrix on the left side, then you're done. And you've now shown that this is now the inverse matrix that we were looking for. And you found it. Now, to solidify everything that just happened, right? And this is where it gets, I have to make sure that I'm not losing people on this because it's rough. But it's not bad. I don't know why I said that. It seems that way. It's really not. So maybe we're going to get plenty. Trust me. I'm not just ending it on this. I wouldn't say that. So let me show what's going on here. This is the Gauss Jordan operations. Right. And if you multiply, right, because now look at this. We started with the ones and zeros over here, right? We had A times identity, didn't we?
Right.
And then we ended with identity time, just kind of split. I don't say I have to say times, but kind of augmented there. Augmented means that every operation you do to one happens to the other. That's what this augmentation bar is. Now we just found the inverse matrix. Now, I want you to look at this. If we started with, and I'm just going to use notation. If we started with matrix A, like just keep it plain here, equal, say, X vector equal to B vector. I'm going to show you why it works now. And I take the inverse matrix that we just found on both of them. It's very important to distinguish form between the intermediate steps that got you there, these being the operations, right? So now look at this. If we do that and multiply it and take the transpose of vector B, then we get the solution x vector, which was equal to xy, remember? And now we have proven, or we'll find that solution once we multiply it. Since we've done matrix multiplication, we'll put that inverse in there. So I've got the inverse matrix now that we just found. I just use they're not parentheses, they're just long brackets. I'll just call them curvy brackets, matrix brackets. So now we multiply it times the 511 that we started with. So we just, remember, we kick that up 90 when we multiply it. And if you notice, that's a 2 by 2. It's a 2 by 1. It's going to work, right? Because the rows now, because the column, the rows become columns when you drop them through. That's right. Because the dimensions are the same. Good job, that one. We proved that in the other video, didn't we? So now, if you multiply this on through, and, what you'll get is this. So let me show that work real quick. So we're going to say that x, y, which is just the vector x, of course, is equal to, that is the same thing. This is the same thing here. I'm just kind of, you can use whichever notation you want. We really don't have to do x, y, but most people just do the x vector because it's easier to write. So then you've got 5 times negative 2, 3 halves. They kind of act like scalars now, kind of. Now we got 11. That's right. And we'll end up with a 2 by 1, won't we? Because it's the outside dimensions that you get. Because every element, we went over that the other, why this method, why Mr. Adam Smasher's method works best, right? Because you could just do this, which is nice. So now you've got negative 10, t over 2. You have to add that vector to this vector. And so now we'll get 1. and 2. Now let's go back earlier, right? So on the previous page, that's what that was here. So if we just did Gauss Jordan elimination without finding the inverse, we would get that same thing.
Yeah.
But let me show it. Let me show why that works, just doing the same thing, right? So now I'm going to show why you get the same answer. Yeah, negative. What was that?
13 half plus negative plus a negative 11 over plus negative 11 halves.
What's your question?
So
What are you asking?
15 halves plus.
Yeah, 15.
Negative.
Yeah, 15 halves plus negative 11 halves. You're just adding and subtracting halves. You get 4 halves, which is 2.
Okay, that's all I'm gonna do. That's me.
Yeah, you're good. Gotta think fast, Padawan. Gonna have set phasers of stun, like train you like Ahsoka from the Clone Wars. So here's the deal. Very unconventional. Just kidding. So here's the deal. All right, so we're gonna go ahead and I'm gonna use the same operations. Take that from the other slide, so that I can prove that nothing has changed. So now I'm just going to use Gauss Jordan elimination without using that method. So let's just do that. See what happens. So now I'm going to show you if we just simply now just augment the vector b, and I want you to pay close attention. If you look over here on slide 1, that's what this is here. And what I'm saying is that now this would not necessarily be correct. This is like an intermediate state, right? What I'm saying is that every single operation will get done to that vector b. Let me show that. It gets conserved. And that's why Gauss Jordan works without having to find the inverse matrix itself. You are finding it without even knowing it when you do Gauss Jordan. So let's go through this. So we've got 1 and 2 and 3 and 4. We're going to augment that with, and that means every operation gets done to 5 and 11 as well. What I'm saying is that if you multiply the A inverse, which absorbed all of these, and multiply it times 511, you would get that 1 and 2 like we got earlier, respectively. So let me show it. So if we do the first operation and just augment it with the column vector right off the bat, then one of these operations here, negative 3 plus row 2 to row 2, you get 1, 0, negative 2. That stays the same. That's negative 15 plus 11. So yeah, negative 3 times 5, negative 15 plus 11 gives me, negative 4, right? It's entirely okay to make a mistake. Keep your augment bar, right? And then we'll do the second one, row 2 divided by negative 2. So keep this top row. It's going to be a 2. It's going to be a 1 now. That stays 0. And let's go to the next. Negative row 2 times 2. So 1, this stays the same. Something's not quite right. Oh, to row 1. Got it, never mind. So that means 0, 1 stays. Negative 2 times, okay, of course, 0. Negative 4 plus 5 is 1. Look at that. Guess what? You just found the answer. You see, and we didn't even find the inverse matrix. So technically, we're saying that once this is done, once we do reduced row echelon form, and that is Gauss Jordan elimination. Like, you can call it REF, reduced row, whatever. And we're doing that on that to get our answer. So that's kind of what's going on here. Okay, now it's really interesting to see this done in other things like Mathematica and so on. Let's see. And I'll have to copy and I'll have to snip because what's going on here? Because I can't show it. Step by step, so my apologies there. Let's see. Anyway, that's it for this, and I'll do a video on matrix, like how to do it in Mathematica, so that, or Wolfram Cloud, however you want to say it, to kind of help this along. And hopefully that helps, and that's just using Gauss Jordan elimination and showing why it works in your operations. Now, if we had done, I just want to make it clear that every single one of those steps, and everything that we did, that if we multiplied that in this, these steps do become the inverse matrix. That's what it becomes, these from the numbers that were given here. So then if you multiply that times the column vector, you are doing those operations on that vector. And that's why this method also works. So I hope that's evidently clear. I think it would be trivial to go through why that works, just because effectively, let's see, you wouldn't really need to do that. In fact, it would be wrong to kind of double dip the method. You got to pick one. But regardless of either way that you do it, I've shown the only two possible ways to go through that. That's Gauss Jordan and the inverse matrix, and why Gauss Jordan works by itself.
Anakin, Chancellor Palpatine is evil! From my point of view, the Jedi are evil! Well, then you are lost!
This is the end for you, my master. Ninja vanish!